So in this video, I'm going to review average value, then go to mean value theorem for integrals, and then go through some easy examples of using anti-derivatives or using derivative rules to find anti-derivatives. So I would get your 5.3 notes packet out because I'm actually going to complete those notes for you in this video. So remember, your homework is on the front of the packet. Average value, that's a formula up there, so you take the integral. And then you're actually taking the integral, show you what you're really doing, and you're actually dividing by b minus a. But since it looks funny, we actually just multiply by 1 over b minus a instead. The other way to look at it is we learned how to evaluate the integral. You find the antiderivative, evaluate it at b, take the antiderivative, evaluate it at a, and subtract. So this, in blue, would also be the average value formula. So I just divide by b minus a, which is the width of your interval. So I did this problem in class the other day. You were asked to find the average value of this function. So the average value of y would be y 1 over b minus a, integral from 0 to 3 of 1/2 x squared dx. So that would be 1/3, because it's 1 over 3 minus 0, integral from 0 to 3 of 1/2 x squared dx. So I'll do this quickly just to give you a reminder of how to do it. First thing I'm going to do is find the antiderivative, and I'll do that back here. The antiderivative would be 1/2. We're going to take x, raise it 1 power, and divide by that power, which would give me multiply by 1/3, and that will give me 1/6 x cubed. So f of 3, which is the b, gives me 27 over 6, which is 9 over 2. F of 0 gives me 0, and when I do the subtraction, I get 1/3 times 9/2 minus 0. Therefore, my answer would be 3/2. So this is a y value. What that means is you can physically graph it on your graph. That would be my y value. If you draw a horizontal line and then you create the area underneath that y value as a constant, that area will be the same as the area that's shaded under the curve. So if I was to melt down the purple area and create a rectangle, you would get that red rectangle. So the average value gives you a y value that would give the same area if the function was a constant, which means graphically a rectangle. So moving on, we are going to look at the differences between the formulas and when to use each, because that's what gets confusing. So the average rate of change formula is something you've already seen. So this gives an approximation for slope, which means it's an approximation for the derivative. Over here, the average value of function f gives us 1 over b minus a times the integral from a to b of f of x dx, and that will give us a y value, the f value. So looking at given f of x, when you use the average rate of change formula, it's to find an approximation for the slope. Average value formula, given f of x, will find a y value on f of x. So that's a difference. One finds a slope, the other one finds an actual value on the function itself. So if I want to do average velocity using a rate of change formula, velocity is position's rate of change. So you take the slope of position to get average velocity. So this says the slope of position. Now, if I'm given velocity, let's see, if I'm given that I need to find the average velocity, but I want to use an integral, you'll notice that it's 1 over b minus a, and the function I'm going to integrate will be itself, the velocity function itself. So using that same exact mode of thinking, if I want to find the average acceleration, whose slope is acceleration? That is velocity slope, which is why I use this formula. Okay, slope of velocity. And then If I want to find the average acceleration using the average value formula, you always use itself as the function, a of t dt. So velocity, to find average velocity, we use the average value formula. Same thing here. Given the acceleration function, if I want to find the average acceleration, if they're the exact same function, you'll use an average value. If I'm given position, but I want to find velocity, that's one derivative, which is why here we use a rate of change formula. If I'm given velocity, but I'm asked to find the average acceleration, same thing, I'm just going to do a rate of change formula, slope, to find it. So in summary, we would end up having that average value is used when the function you are given is the one whose average you need. Okay? And then average rate of change is a slope. So we use that when the average needed is the derivative of the given function. So I'm going to do an example from your packet. So it says that on top I just reminded you to use your calculator. You can use it to check your answers. Usually for these I still want you to do them by hand, but we would be able to check our answers for average value by integrating using fint and then dividing by b minus a. So it says find the average velocity. So I want to find the average velocity, and in this case I'm given velocity. Since the function I'm given and the average I want are the same function, that means I'm going to use average value formula. Which means that the average velocity would be 1 over, and I actually need to give you an A and B. So let's do from 0 to 2. Let's do 0 to 3. Okay. So 1 over b minus a, integral from 0 to 3 of v of t dt. So what do I need to do? Find the antiderivative of the original function, which is 4t squared. So that would be 4t squared, which would go up to 3, divide by 3, minus 6t, raise it by 1, divide by that same power. And then I would need to find f of 0 and f of 3. But I'm going to actually go from b to a. So everything's kind of in a nice order. So f of 3 would be 27 divided by, so divided by 3 would give me 9. 9 times 4 is 36, minus 3 squared is 9. 9 times 3 is 27. And hopefully I get this right, and that the answer for f of 3 is 9. F of 0 would be 0. Let's really hope I did that correct. Therefore, the answer to this problem in red will be 1/3 times 9 minus 0, which is 3. So what did we just figure out? We found out that if I was to graph the velocity, and I found the area under the curve, the net signed area, I would find that if I make a horizontal line at y equal to 3, that area of the rectangle will be the same as the net signed area underneath the curve. Find the average acceleration. So in this case I want this. If I want the average acceleration, but I'm given velocity, that's one derivative, which means I'm going to use the slope. So I would use the slope of velocity to do such things, and then the average acceleration would be v of 3 minus v of 0 all over 3 minus 0. So average acceleration would be, if I substitute in 3, square it, you get 9. 9 times 4 is 36, minus 3 times 6, which is 18. So that's v of 3 minus v of 0 would give me 0 all over 3. So 36 minus 18 is 9. 9 divided by 3 gives me 3. So the average acceleration actually gives me the same answer as the average velocity, which usually does not happen. So hopefully I actually did this right and I didn't make any kind of numerical mistakes. If I did, please email me and let me know, and I'll try to see if I can go back and fix it. All right, moving on. Mean value theorem is very similar to what you learned for mean value theorem for derivatives. So you find your average value, and it says that there's a C value such that the Y value at that X will be the same. So Y value is the same as the average value. So if you remember the problem from the average value, I put the graph back to the right again, and if you remember, we actually found the average value of that function. I think I called it y. 3 minus 0, integral from 0 to 3 of 1/2 x squared dx, and that was 3/2. So what this says is there is a value, meaning y value, of the function 1/2 x squared such that it is equal to the average value. So this is the function, this is the average value, and they will be equal somewhere on the interval. It means that you're guaranteed once, but it could happen more than once. So if you look here, on my interval from 0 to 3, here's my 3/2, and obviously the intersection happens here. So how would I find that intersection? I would solve the equation that is right here, and that would get you the exact x value for which the rectangle area is the same as the net signed area under the curve, which would be the red area. Okay, if I melt the red area, it would melt down to a rectangle that would be the exact size of the purple rectangle. So that is a very, very fast review of average value and the mean value theorem. So now I'm going to look at some basic derivative rules. Actually, before we do that, we are going to use the table of values to find the upper and lower estimates of 0 to 10. Assume that f is a decreasing function. So I put these in for us to discuss. So I actually want to discuss those in class on Monday. So this will be done on Monday. If I forget, someone please remind me. Okay. Finding antiderivatives using derivative rules. Let's start with some basic functions that we already know. So we already learned the power rule. So the integral from a to b of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c, because we did the opposite of the power rule. So right now, you will only be able to do integrals of basic derivatives. So what do I mean by that? Let's see, if I gave you something like this. You would have to figure out whose derivative is this. And obviously the answer is sine's derivative is cosine, therefore sine of x plus c would be the answer. And then we can go over here and do the integral of sine of x dx. And most people want to say it's cosine. But if you think about it, cosine's derivative is negative sine of x. Therefore, whose derivative would give us a positive sine of x? It would have to be negative cosine of x, and then plus c, of course. Then we can get even more difficult, and we can do the integral of negative 1 over the square root of 1 minus x squared dx. That should look familiar, and hopefully I wrote that rule right. Whose derivative is that? That is cosine inverse its derivative. And then show you one more before we get to that page. The integral of secant x tan x. And let's even put a 2 in front of it. Dx. Well, you should be able to recognize that that is secant's derivative. And the 2 we can pull out. So let's get rid of the 2. rewrite the problem, and then you should be able to figure out that the integral of secant x tan x is secant x. Therefore, here's your answer. And then we'll do one last one. The integral of, let's say, 4 over x dx. So same thing. Bring the 4 out front. Then I'm left with this guy, whose derivative gives us 1 over x. That would be ln of x. Therefore, 4 ln of x plus c. So that is how you are evaluating the antiderivatives of integrals, because we're just looking at basic rules. So we're not really dealing with chain rule yet. We're not dealing with product. We're not dealing with quotient. So please just be reminded of that. You're really looking at basic rules. So here, I would say most of them are basic rules until you get to these two. They actually have a little bit of a chain rule inside of there. So I would be very curious to see who actually gets those right. So these, I think this is the worksheet from homework number 7. And that should complete everything you need to do, or need to know, sorry, for homework number 6 and part of 7. I'm actually going to make another video for total area versus net signed area.